me ouvem, se devo usar. Olá. Não sei se me ouvem, se devo usar o microfone. Como foi dito, portanto, eu sou Paula Vilarinho, venho do Departamento de Engenharia Sistémica e Inovativa da Universidade de Aveiro e sou investigadora do Ciência. E a minha palestra hoje é acerca de Design of Nanoporous Functional Perovskite Chemicals. A apresentação foi preparada para ser feita em inglês e, portanto, neste momento estou na dúvida exatamente qual é a língua que devo utilizar. Há algum estrangeiro na sala? Pronto, provavelmente será. Provavelmente há. Ok, so I will do it in English. Okay. I'm ready to do it in English. I'll do it in English. So the talk is entitled Design of Nanoporous Functional Perovskite Chemicals, and I'm going mainly to present the work that we have been doing.
Paula, desculpa interromper, mas para ficar gravado tem de ser no microfone também.
Não posso sair daqui? Okay. This is going to be mainly about ferroelectric thin films. And first, I would like to thank the organizers for inviting me and giving me the possibility of showing some of the work that we have been doing. And I should say that this is a work that has been done in collaboration between the University of Aveiro and the University of Pierre and Marie Curie in France. Okay? Desculpa. Tá. Não tá. Ok, não tem problema. Não tem problema, uso aqui. So I will start my presentation by framing the work and trying to explain the motivations why we are doing it. Then I will proceed and I will present two cases that are currently under study. And then I will conclude by trying to present what we have learned until now. So the question here is, why are we worried about nanoferroelectrics? There's a few reasons behind, and I will try to explain them. Because this is a nanotechnology or nanomaterials session, I will skip this nanostructure classification, and I will go a little bit more into the material in order to explain why this material is important. So for those of you that are familiar with ferroelectrics, ferroelectrics have a very particular property. They have a spontaneous polarization. This is particularly important, especially because we can reverse the polarization by changing the applied field. This allows us, from a certain point of view, to save data. So the most important application of ferroelectrics are related with memories, electrically controlled memories. So that's why they are particularly important. There are a few materials with I would say, a huge range of materials with ferroelectric properties. And among the inorganic ferroelectric materials, barium titanate is a kind of a prototype. So I'm trying to justify why we are working on barium titanate. It's a prototype ferroelectric material. I will talk a little bit later on it again. Okay, so besides this possibility of switching the polarization, ferroelectrics have very high dielectric permittivities, very low losses. They are piezoelectrics, they are piroelectrics. So this justifies the huge range of applications that we use every day, okay? Being one of the most important, the use in non-volatile memories. Very simple example, radio frequency identifiers use non-volatile memories, and they should even use more. Some of our computers, some of our mobile phones, many electronic gizmos, they use non-volatile ferroelectric memories. Okay. The step further, so as I said before, these are the current or the present applications. But in terms of future, microelectronics industry is requiring many, many things. And I think that everybody knows that we are trying to minimize all of the electronics devices. But it's not only minimizing, making them more mobile, making them with faster communications, and functionalize them. There will be no Internet of Things if there will not be microelectronics with the required properties. Okay? So how to do this? There are different ways. Different ways have been tried. And one of them is, should we try to get these things smaller, nano-size them? Okay, so in the majority of the examples, as all of you know, we have modifications of the properties when we decrease the size. In the case of ferroelectrics, this is not completely clear until now. Okay? This has been attempted for a long period of time, and this graph tries to explain the importance of ferroelectric thin films because these were the first attempt to decrease the size, so decreasing the thickness of the layer. This becomes particularly important in the 80s, when it was possible to prepare films with reasonable properties. There was a group of companies that become interested in them to use them as a practical device. First ferroelectric random access memory appears in the market in the beginning of the 90s. And since that time on, we are still discussing how to improve, how to decrease, how to understand the size effect. Few things. When we try to decrease the size, the properties generally decrease. So, I would say worst properties. I'm not going to go into details. And the reasons are related with defects, stresses, all of the things you know. However, and also, this somehow hindered the capacity or the capability of understanding what are the intrinsic effects that have been changing. Okay? However, not everything is bad, so there's a couple of opportunities in terms of ferroelectric thin films. Few properties that were non-existent and they were somehow induced by the stresses, and by improving the processing, it's indeed possible to get very similar properties to the bulk. Okay, moving on. More recently, it was predicted that when we prepare 1D ferroelectrics, we are supposed to have enhanced properties. Until now, this is not completely proved. There's a few studies, and this is one of the recent studies that somehow is related with CSECO, so that's why it's here, in which these PZT tubes, the ferroelectric piezoelectric material does matter, they show a very intense terahertz emission, and because they are ferroelectric, there is the possibility of having these emissions controlled by the electric field. So that's why this result is interesting. Another interesting prediction is that when we are dealing with 0D ferroelectrics, different properties such as the polarizing fields along the 3 dimensions and toroidal moments are predicted. Nothing has proved until now. And then I forgot to say that for this particular application, ultra-high storage density for memories is expected, but nothing is proved until now. So we have been doing a couple of things in terms of nano-size structures in ferroelectrics. We have been preparing, nanobelts, nanorods, nanotubes, nanorings, nanoisland. Many things have been done. The properties are not completely clarified, but a few things have been done. We have been changing size, shape, surface, and many things. We are trying a different approach, and that's exactly what I'm going to show to you. So we are trying to use porosity. And why porosity? Usually porosity, in terms of electrical properties, is usually considered bad. The majority of the time, porosity decreases the properties of the materials. But we are trying to use it. The reason why, something is wrong here. It's not working anymore. Okay. It is known, porosity is known for a long time, and there are many interesting applications for porous materials, as you know, so everybody is familiar with this. From filters to catalytics, fuel cells, scaffolds for bone replacement, and there are a few ways of preparing them. So in terms of bulk, this is quite known. In terms of dielectrics, although the majority of the times the properties are bad, are worst, there are few situations in which we can somehow improve by having highly isometric dielectric properties. So I'm talking about bulk dielectrics. Also known are the tunable 3-dimensional photonic crystals that are prepared with invertible pile ferroelectrics with very organized porosity, as it's seen in the picture here. And the other thing that we know in terms of bulk is that for pyroelectric applications, the figure of merit of a pyroelectric sensor increases with the porosity. So there's a few things that allow us to say that porosity is not always bad. First, first thing. And we think that if we organize it, it can be used maybe to tailor the losses of these materials, that are something very important. And also, we may use this kind of metrics for functionalization. So we are expecting to have functional materials, I would say in some situations even some metamaterials, that may happen by the use of porosity. And the other thing that we are trying to do is trying to develop methods, usually low cost, that allows this type of materials to be, I would say, used in real devices. Okay? So our approach is to design materials from the molecular level and with controlled porosity in a wide range for now. Then maybe we'll shorten it, and with a high surface area ordering, and then get pores ready for functionalization. Okay? Among these, there are two main methods, and I'm not going to into detail in details because I don't have time. So there are two main methods, soft templates and hard templates. We are using soft templates in which we are using some micelles, and we are using some block polymers, okay? So the way we prepare our films usually is by deep coating and by a very controlled evaporation. And after that, we heat treat these materials because they need to crystallize. If they will not be crystalline, then the properties will not be the best. So that's exactly what this slide shows. And then by the end, we control the nanoporosity and sometimes the mesoporosity of our films. Okay, so some results. Como é que está o meu tempo? Okay. So some of the results. I will start with lead titanate, and I will briefly say why did we start to study lead titanate. So lead titanate is one of the most important ferroelectric materials because it has a very high TC temperature, QT temperature. And there are few applications currently that require high TC materials. 1 point. Second statement is that it's very difficult to keep lead titanate as a bulk material because it has a very high volume change when it goes from the ferroelectric to the paraelectric transition, or the other way around. So keeping it in its, I would say, lattice at nano dimensions, it will be quite interesting, okay? So we have been preparing a few films, and here they are represented. Films with 1 layer, films with 2 layers, films prepared with concentrated solutions. We have been playing around, and we have been able to somehow tailor the porosity. You will see later that in other cases we get this in even better. So this is a dense film prepared in the same conditions without not using the block of polymer. So these materials, as I said before, they need to heat treat it because we need to crystallize the phase. So here is the effect of the temperature, and of course the porosity is somehow modified, but we are able to keep it not exactly so well defined, but we are working on this. Very interesting is that we keep the ferroelectric properties of these materials. So we are using a scanning probe microscopy, in this particular case piezo force response microscopy, to assess the local properties of our films. And this is a perfect hysteresis loop for a PT film. So the porosity is not affecting the response of our films, okay? Barium titanate, as I said before, it's another ferroelectric prototype material. In this particular case, it's lead-free, and because it's lead-free, it's quite interesting. It's one of the most common materials to be used in high-density capacitors. Okay, here is some of our nanoporous films. In this case, we were able to have pore size around 50 nanometers. We can control this, and we are controlling this. The type of microstructure or nanostructure that we obtain is very dependent on the concentration of the polymer. So when we change the concentration, of course, we change the microstructure of our film. And also when we age the solution. So we have a few aged solutions and studies ongoing in order to try to understand the best way of preparing the films that we want. Okay, these films, as I said, they require heat treatment to be crystallized, and these temperatures, as you can see, reasonably high. We have the phase formed at 625, that it's quite good. At this moment, we are not worried about decreasing this temperature, and our TEM results show clearly that our material starts to be crystalline at around this temperature, And here is the effect of the microstructure, of the temperature on the microstructure, in which we can, for the highest temperature, keep the porosity where we want, okay? Again, we need to access the electrical response. So in this case, we have a domain imaging, in which we have domains black and domains white. This means we have the polarization to the top or towards the surface of the film. And here is the hysteresis response of these materials. Again, the porosity of these films is not affecting the electrical response. So what we are doing now is trying to use these metrics to design our materials. And we are doing this by impregnating these structures as they are represented here, for example, with ferromagnetic entities. We have been playing around on this. The idea is not only to stick on the ferroelectrics, but I think the community knows that there's a very big need of multi-ferroic materials. So that's the reason, that's exactly what we are doing. We are trying to, I would say, fill these gaps with different ions and different materials. Okay, so I'm on time, right? So we learned a couple of lessons. So we learned that it's possible to organize nanoporosity in typical ferroelectric thin films by a very simple and low-cost chemical process. We also learned that depending on the conditions, of course, all we know, we can control this nanoporosity. And interesting is that we keep the properties even with the porosity that we are inducing. That's something important in terms of applications. Okay? These nanostructures are now being used as metrics for nanocomposites. And at the same time, we are trying to do some lattice, structural lattice studies in order to understand how we can control properties as losses, dielectric losses with porosity. Okay, so we think that we are, I would say, targeted to get materials that will allow us to go into these smart microelectronics that are very required nowadays. Thank you, and obrigada.
Thank you, Paula. So now the session is open for discussion. We have time for 1-2 questions. Yes, please.
I think you, okay, fine. So that's the point. Another statement is that there's a huge funding and effort to substitute lead. The most active country in terms of research is Japan, in which they have, I would say, 3 years to substitute lead-based materials. And this time is ending, and there's no solution yet. Now going to barium titanate. So both of them are prototype perovskite cubic structures, which I would say some of the best properties. The lead titanate is very difficult to use as a bulk because during the phase transition it exploded because it has a very high volume change. Barium titanate is used since the last Second World War, okay? It's not the best material. So that's exactly what the Japanese community is doing now. It's improving the properties of barium titanate to substitute PZT. So why did we start doing this? Of course, lead-free is something that we have in our mind, no doubt on that.
Paula.
But at the same time, lead titanate can still be used, and it's going to be used for a while, and we will learn it, because many things are
Paula.
known from them, okay?
Sorry to interrupt. Can you shorten up a little? We are
quickly.
way
The
behind schedule.
the end of the question. We didn't compare the performance as a device. We compare locally, and as we expected, PT is better than BT.